The figure below shows a setup for Atwood's machine. M1 is connected over a pulley to a container of water. So that is M1 and that is the pulley. It is connected to a container of water whose mass M2 is a function of time, because the water in that container rushes out downward at a constant rate of c kg per second with velocity u meter per second. The initial mass of that container of water is m0 kg. We want to determine the acceleration of the system as a function of time. The mass of the pulley and cable can be neglected. So let's look at the free body diagrams of these two masses. The first is m1. So that is m1. All the forces that are acting directly on m1 is of course its weight and tension, which is going in an upward direction. So the weight is m1g and the tension is capital T. And let's assume the direction of the acceleration is downward. Now we note that acceleration is a function of time because the other mass in the system, m2, is decreasing with respect to time as the water rushes out of the system. Applying Newton's second law to m1, we get m1g minus t, which is the net force acting on m1, equals to its mass m1 times acceleration at. So let's call this equation 1. So let's write down that equation 1 and put it in a box for later use. Now let's look at m2. The forces acting directly on m2. The first one is its weight, m2g. The second one is the tension in the rope, that is this rope right there. And there is a third force. Note that water is rushing out downward, like that. And it rushes out with certain speed u. So the rate of change of momentum here, which we can write as dm times u over dt, since u is constant and that can be taken out of that derivative sign, is u times dm dt. However, dm dt is c, which is a constant, so you can simply write it as u times c. This rate of change of momentum, which in fact is a kind of force, creates an upward thrust on m2, and that we have to label in a following manner, and that is u times c, and the acceleration is a in an upward direction. So there we have it. Applying Newton's second law to this mass m2, the upward force is T plus u times c. The downward force is its weight m2g, so the net force is T plus uc and minus m2g. So the net force is in an upward direction, and that is m2 times a, which is a function of time. So this is equation 2. Since we have understood that m2 is also a function of time, let's write m2 in terms of m0, which is the mass of the container of water at t equals to 0, and c, which is the constant rate with which the water rushes out. That is an easy task. Since the rate with which the water rushes out, let's call it dm dt, that is just c. The water loss at any time t can be obtained by simply integrating this equation. And you're going to get m as a function of time equals c times t, plus an integration constant, let's call it capital E. However, at t equals to 0, the water that is rushing out is 0. So the integration constant capital E goes to 0. So the water that is rushing out at any given time t is given by that expression. That means m2 as a function of time is quite simply the initial mass, which is m0, minus m as a function of time. And that is just m0 minus ct, because m as a function of time is just c times t. You see that when t equals to 0 in this equation, that gives you m naught. So m2 at t equals to 0 is m naught. So the equation for m2 as a function of time that we have obtained here agrees with the given condition. So let's call this equation equation 3. So here are all the three equations. First, let's try to solve the acceleration by eliminating the tension. And for that, we need to take equation 1 and add that to equation 2. When you do that, you see the left-hand side contains minus t for equation 1 and t for equation 2. So by adding these two equations to each other, the tension T can be eliminated. So the left-hand side would become m1g plus uc minus m2g. And the right-hand side is m1a plus m2a, where we know a is a function of time, m2 is a function of time given by that expression. And from the resulting equation, we can immediately solve for acceleration. And you get acceleration as a function of time equals g times m1 minus m2 plus u times c divide by m1 plus m2. Now let's substitute the result for m2 as a function of time from equation 3. And that's going to give you the acceleration as a function of time in a following form. G, the top one, m1 minus m2, is m1 minus m naught plus c times t, don't forget that term, plus uc over m1 plus m2, which is m1 plus m2, so plus m naught minus ct, thus giving you the final answer for the acceleration of that system as a function of time in known quantities. And that solves the problem. As always, thank you for watching.